Hello everyone, my name's Steve Chapman. I'm the Vice-Chancellor of Edith Cowan University, and thanks for coming along today. I want to welcome our distinguished guests. We have Professor Dan Shechtman and his wife Zipporah Shechtman. Great that you could make the time to come and see us, Dan. Thank you very much indeed. Before I introduce Dan, I'll let Dr. Noel Nanup, ECU's Elder in Residence and Cultural Ambassador, perform the Welcome to Country. Noel.
Kaya, Bridia Marman. Wow, awesome to be back. I often get this opportunity, and I think one of the beauties of it is it gives us a chance to just begin to relax and settle into our seats and unwind. It's a pretty hectic world out there, moving at an incredible pace. As we do that, on behalf of the Whadjuk people, my father's people, I have the honour of welcoming you onto country, particularly our guests that have travelled a long way to be with us. It's extra special. And in their honour, I will tell you why we do a welcome to country. As people travel across country and go to different places in our way and our ancient world, people do go to somewhere where they may not know, and they pick up spirits, and those spirits travel with them. Obviously, this is our belief, and it's something that's been in place for so long that Australian Aboriginal people are now recognised as belonging to the longest continuous unbroken culture of any race of people on earth. So as we do this for you, if you're born here, your spirit comes from here. Obligation is to care. If you're born somewhere else and you lived here more than 6 years, then obviously the spirit knows you. If your intentions are to stay, then you're obligated to, and that is to care for everything. And in this instance, we have our visitors. There may be more of you that were born elsewhere and have lived here less than the qualifying period. And in that instance, the welcome is to keep you safe during your time here, even though you may not be in the presence of the person that welcomes you. So I say, Kaya Bridia Marman, Kaya Bridia Yogas. It's awesome to have this opportunity as we begin to really settle in now. Wara wern bolyakangan. We need the bad spirit to go away. That's what wara means. Wern is the spirit, bulyakan is to go, and ngan is from me. Wara wern bolyakangan. Hopefully, I have sufficient humility to fill the void that's been left by the bad spirit as I ask the good spirit to come and sit with us. Kwabardan jinjit, ngaladat nyaning. Good spirit, come and sit with us and on us. My ancestral lineage here takes me back many thousands of generations. Wanju wanju, lecha. Whadjuk nyunga budja. Welcome to country.
Thank you very much for that, Noel. So, ladies and gentlemen, each year ECU invites an eminent person to deliver the Vice-Chancellor's Distinguished Oration. And this afternoon, we're very honoured to welcome Professor Dan Shechtman. Now, Dan is the Philip Tobias Professor of Materials Science at the Technion, Israeli Institute of Technology. He's an associate of the US Department of Energy's Ames Laboratory and a Professor of Materials Science at Iowa State University. Now, I'll go back a bit and tell you about his career in a moment, but of course in 2011 he was awarded the Nobel Prize in the most important subject area you could be awarded the Nobel Prize in, and that of course is chemistry. And he was awarded the Nobel Prize for his discovery of quasi-periodic crystals, or quasi-crystals. And actually, if you think about the crystalline arrangement of atoms, that means that you can have a structure that is ordered, but not periodic. And as Dan will tell you, that really was a scientific revolution because it led to a change in the very definition of what a crystal is. So, a bit about his career. So, after completing his doctorate studies in materials engineering at the Technion in 1972, Dan Shechtman worked as an NRC fellow at the Aerospace Research Laboratories of Wright-Patterson Air Force Base in Ohio. It was in 1984 that Professor Shechtman published his findings on quasi-crystals, quasi-periodic materials, for which he was recognized with a Nobel Prize 27 years later. So it took a while for the rest of the world to realize just what Dan had actually done, and he'll explain that to you. Dan's a member of several academies, including the US National Academy of Engineering and the Israeli National Academy of Sciences. He's an honorary member of professional societies around the globe, and is the recipient of many prizes, including the Wolf Prize in Physics and the Grigory Arminov Prize of the Royal Swedish Academy of Science. Now, Dan's going to speak to us for an hour, probably exactly, because he's a very precise guy. And after that, we'll have a few minutes for questions. So, without any further ado, please join me in welcoming Professor Dan Shechtman. Thank you.
Thank you very much for this introduction. I assume that most of you are scientists and students of science, but if there are lawyers here too, you will understand me, because my talk, on the one hand, is very, very simple, and on the other hand, it describes a very complicated issue in science. So, the subject is quasi-periodic materials, a paradigm shift in crystallography, and I would like to mention one thing before I even start. There is nothing quasi in these crystals. They are real crystals. The name quasi-periodic comes from mathematical equations, which are quasi-periodic mathematical equations, which are related to this subject. That's all there is to it. The rest of it, they are just as crystals as any other crystals. So let us start. Let me take you now to the mid-80s. And in the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties. And they came year after year, and all 3 of them received the Nobel Prize later on. The first, chronologically, was the discovery and announcement of quasi-periodic crystals. My name, Ilan Blech, Denis Gratias, and John Kahn. I will tell you about these people a little bit later on. Next came the discovery of fullerenes. Harry Kroto and his colleagues discovered the fullerenes, and a year later came the discovery of high-temperature superconductivity. Now, when high-temperature superconductivity was discovered, there was no resistance, there was no objection to the discovery. Everybody was happy. Hey, for so many years we had superconductivity since 1908, but now we have high temperature. Instead of liquid helium, we can use liquid nitrogen. Wonderful. When fullerenes were discovered, Harry Kroto and his colleagues met some resistance, some objection to the model, and Harry tells me that there were 6 papers objecting the model, but the rejection died very soon. But when quasi-periodic crystals were discovered, they met a lot of resistance from the top of the scientific community in the world. And that objection, that rejection lasted for a long time. I will tell you about it. Okay, now in order to understand my subject very well, I will take you back to the basics of crystallography, just very basics. And I will talk about order, I will talk about periodicity, and I will talk about rotational symmetry. Let's talk about order in crystals. Here is a two-dimensional crystal, and clearly it is ordered. What does it mean to you? It means that if I ask you to continue it in this direction or in any other direction, you know how to do that. It's very simple to continue this structure. This is order. It has an order. Now, what about periodicity? Look at this red line. Clearly, you see that there is periodicity here. The distance from here to here is the same as from here to here, and so on and so forth. And because this structure is periodic, there is periodicity in every direction that you may choose. Like in this direction, there is periodicity. In this direction, there is periodicity, any direction. That's all about periodicity. What about rotational symmetry? Here is this structure again. I added a little handle here, and I can turn it 90 degrees, and it looks the same. 180 degrees looks the same. 270 degrees look the same. And 360 back to where we were before. And you can do it 4 times, and each time it looks the same. It means that this structure has a 4-fold rotational symmetry. That's it. Okay, this is the basic. Let's say a few words about crystallography. Modern crystallography started in 1912 with the very important discovery of von Laue, a German scientist who discovered X-ray diffraction. And from there on, the tool of X-ray diffraction became the tool of choice. The tool became more and more precise, and the number of crystallographers, modern crystallographers, grew, and a society was formed called the International Union of Crystallography. This society is composed of no-nonsense mathematical crystallographers. These people have to show from the very basic that everything is correct in the science. They are the rulers, and the tool of choice was X-ray diffraction. Not electron diffraction, not neutron diffraction, X-ray diffraction. And later on, you will see why it was so important. Okay, the crystals von Laue studies were ordered and periodic. And all the crystals that were studied ever since, until 1982, for 70 years, hundreds of thousands of different crystals were studied, and all of them were ordered and periodic. There was no exception. And this is why, based on this observation, a paradigm was created that all crystals are periodic, and the following definition of crystal was accepted by the community of crystallographers and by the scientific community in general. So what was the definition? This is a crystal. A crystal may be defined as a solid composed of atoms arranged in a pattern, periodic in 3 dimensions. What can be simpler than this? Periodicity and order. Order and periodicity were synonyms in crystal. Another definition from another book, exactly the same meaning, only different words. Atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Exactly the same meaning. Crystal is ordered, a crystal is periodic. Crystallography in 1982, which is the year of the discovery of quasi-periodic materials, here's an example. This is a book by Charles Kittel. Many of you know this book. I studied this book. And it's called Introduction to Solid-State Physics, and I marked something in green here, and I know that some of you cannot read it, and this is why I've enlarged it for you, and now you can. So it says the following. We can make a crystal from molecules which individually, each molecule, can have 5-fold rotation axis. But we should not expect the lattice to have 5 rotation axes. I've shown you before a lattice, a 2-dimension, with 4-fold rotation axis. But there are no 5-fold in periodic crystals. Now, and I will elaborate on that. Now, let's talk about real space. Real space is the space in which we live, the space where the atoms are. Well, most of us live in the real space. And look here, you can see clearly that there is order here, and you can see clearly that there is periodicity. By the way, these are carbon atoms in diamond. High-resolution microscopy, I took this picture very, very many years ago. Look here. There is periodicity in this direction. There is periodicity in this direction. There is periodicity in this direction. Any direction you choose, you'll see periodicity. The order of carbon atoms in diamond is periodic. The allowed rotational symmetries are 1, 2, 3, 4, and 6. 5-fold rotational symmetry, as well as any other symmetry beyond 6, is forbidden in periodic crystals. And this was clear, and this was true, and it is still true. It's basic mathematics. Okay. Now, let me show you a diffraction pattern from a periodic crystal, which is characterized by periodicity of the diffraction peaks in the reciprocal space. Now, the reciprocal space is a mathematical space which enables us to understand what we see in the diffraction pattern. It's a tool that we have created to understand diffraction patterns. This diffraction pattern is taken by an electron microscope. It is an electron diffraction pattern. What happens in an electron microscope is the following. You shine an electron beam, accelerated electron beam, very short wave, onto a specimen, and the specimen is very, very thin. We make it very thin so that the beam, electron beam, can penetrate through and hit a phosphorus screen. Today, it's a camera, but a phosphorus screen. So the transmitted beam that goes straight through is the central beam here, right here, this little fat point. All the other points are diffracted points from the periodic lattice. And because the lattice itself is periodic in the real space, the diffraction pattern in the reciprocal space is also periodic. And the same rule applies for the reciprocal space. Now, first of all, you see periodicity because the lattice is periodic, and also in this direction, and in this direction. Any direction you choose, there is periodicity, exactly like in the real space where the atoms are. And the rotational symmetries that are allowed are exactly the same as in real space, 1, 2, 3, 4, and 6. No 5-fold rotational symmetry, and nothing beyond 6-fold is allowed. This was in the textbooks. This is what we studied. This is what I studied when I was a student. In fact, when I did my master's degree, I took a class in crystallography, and one of the questions in the final exam was prove that 5-fold rotational symmetry cannot exist in crystals. And I proved it. And I passed that exam, and this is why I'm here now. So, this is history. Now, let me take you to what happened. In 1992, the International Union of Crystallography redefined crystal. You have seen the old definition, now there's a new definition. Now this definition is probably the nicest definition in nature. Let me show you why. Number one, it sounds like a poem. We'll read it slowly. Number two, it takes us to a different world of understanding nature. Right? Let's read it slowly. It doesn't say crystal is. We are humble now. By crystal we mean any solid having an essentially discrete diffraction diagram. Not discrete, no, essentially discrete diffraction diagram. Soft. This is the International Union of Crystallography. I mean, these are the no-nonsense mathematical crystallographers. And they wrote this poem as a definition of a crystal. Let's go further. So, by crystal we mean any solid having an essentially discrete diffraction diagram, and by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. Now, look at it carefully. A crystal is not defined now by the order of atoms. A crystal is now defined by how the diffraction pattern looks like. The real space is defined by the reciprocal space. All has been reversed. This new definition is a paradigm shift in crystallography. And this is why the discovery was so important. Okay, let's go to history first. 1982 was the 70th birth of crystallography. Remember, 1912, 1982, 70 years. And this was the year quasi-periodic crystals were discovered. Now, in order to understand what happened on the day of the discovery, I will take you to my laboratory logbook. And here it is. Now, I want to talk to the young among you. Lessons from this is the following. When you do an experiment, or if you are theoreticians, when you make a calculation, write it in a logbook. You may remember the experiment or the calculation for a whole week, but you will not remember it next year. Make sure it's in a logbook. In most cases, it will just be for you. I thought that this is for me. This is why the handwriting is so sloppy. And it's written in the dark of the electron microscope room. But sometimes your one page in the logbook may be very, very important. Make sure it is there. So this is the logbook. It has a lot of information. The date is April 8, 1982. I was working on an alloy that I have prepared by rapid solidification of aluminum 25% manganese. This is plate number 1720 of the electron microscope. And there are many before and many after. And this is the first book in a series of logbooks. SAD means selected area diffraction. You remember, this is written only for me, so I have to explain you what I meant by that. And I take picture number 1720, selected area diffraction, 21, and then 22 is a picture with 28,000 time magnification, and so on. And then I arrive at picture number 1725. And in fact, 1724 first. I look at this picture and I say, wow, that's interesting. Now, I'll elaborate on that in a minute. I take a diffraction pattern, I look at the diffraction pattern and say 10-fold with recursion marks. Remember, allowed rotational symmetry 1, 2, 3, 4, 6. No 5, nothing beyond 6. 10-fold rotational symmetry. This is impossible. There ain't no such animal. So I'm quite surprised, and I say to myself, okay, what can it be? And I will be very short on this. I thought that these crystals had defects in it, and these defects are called twins. Only a few of you know what it is. And in a twin crystal, you can create such a situation, and this was based on my previous experience as a scientist. So I was looking all the day, by the way, this was in the afternoon, so I spent until the evening taking more pictures, trying to find the twins. And if I would find them, that would have been the end of story. I would file them and forget it. It's not interesting. I could not find the twins. I was a veteran electron microscopist. I knew how to use the machine very, very well. I could not find the twins. They were not there. Okay, so this was the discovery. And when they gave the Nobel Prize, they said that rarely in the history of science you can pinpoint a discovery not only to a day, but to an hour in a certain day. This is it, okay? This is the discovery. This is Mr. Archimedes, when he discovered the famous law of Archimedes. Story tells us that he jumped out of the bathtub shouting, "Eureka!" We don't do that anymore. Today, if you see something that will happen to be later on recognized as a discovery, usually you say, what's going on here? Or, wow, that's interesting. What is this, right? Most of us don't take even bathtubs. We go to the shower, right? Okay, anyway. No showers in his time. So what was so interesting? This is plate number 1724. And this is how it looked like. This is a picture. This is the micron bar, so this is the magnification. I'll tell you what you see here. You see here a polycrystalline material. It's a material that is composed of many little crystals, the size of which is between half a micron to a micron. This is half a micron. So here is a crystal, and here's another one, and so on and so forth, right? About half a micron to a micron. So what's so interesting here? Aha, I knew you would ask. This crystal is pitch black. So is this, and this, and this, and this. I have never, in my previous experience, I've never seen any crystal which is so black. What does it mean, a black crystal, when you look at it with the transmitted beam? It means that the transmitted beam has no intensity. It means that all the intensity goes to the diffraction pattern. And I have never seen a crystal that diffracts so heavily so that there is no intensity, almost no intensity in the transmitted beam. And I say, wow, how does the diffraction pattern look like? So I take a diffraction from one of these black crystals, and this is what I see. So I look at this pattern, and I say, wow, that's interesting. What's going on? What is the rotational symmetry? So I start to check the rotational symmetry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Tenfold. Cannot be. Count again. 1, 2, 3, 4, 5, 6, 7. Tenfold, and I write tenfold with 3 question marks in my logbook. What's going on? And then, I thought it was twins and so on. So this was the electron diffraction from the icosahedral phase. This was the name I have given to the phase, and I'll tell you why I called it so. And the reason is that it had icosahedral symmetry, and I'll talk to you about it. And it has 5-fold rotation axis, and it is not periodic. So, no periodicity. Not only it has, by the way, it's not 10-fold, it's really 5-fold, but I should have done more experiments to see that it's 5-fold. These experiments are called Kikuchi patterns. We'll not go into that. But I was looking for periodicity. No periodicity. All right? Look at the distances. You take these distances, multiply by 2, you get here. And there is nothing there. So, no periodicity. The ratio of distances between the central spot and other spots in the is the Fibonacci number tau. I raise the memory of Mr. Fibonacci of Pisa, and that number is called tau or phi, known also as golden mean. And this is this number, 1 plus root 2 divided by, 1 plus root 5 divided by 2, 1 plus 1.618, an endless number of digits. This is an irrational number. Irrational numbers came into crystallography. And this is this. This is the entry point of irrational numbers that came into crystallography. So if you take the distance from here to the center, divide by distance from here to the center, you will have something which is close to Fibonacci number. Of course, you can never get Fibonacci number by dividing A by B because it's an irrational number. So this was the story. Now, this diffraction pattern was not the only one. You see what you can do in the microscope. You have a goniometer, and you can turn your specimen to any position you want, and you can tilt it to any position you want. So you can get diffraction pattern from many orientations, and this is the series of orientations. So we have 5-fold here, and I turned it so many degrees, and I have 2-fold, and then turn it more, and I have a 5-fold again. So 5, 2, 5, and 5, 3, 2, 3. And this series of symmetries has an icosahedral symmetry. I will talk about the icosahedron in a moment. You'll know everything. So this is the set of diffraction pattern. Okay, this is what I thought I have. I will explain to you now what are these twins that I thought I had. Now, the picture that you see here is a picture of, again, of carbon atoms in diamond, and it has defects. So there are 5 crystals here, 1, 2, 3, 4, 5. But they're not just any crystal, because they meet at a point here, and there are boundaries between them. Boundary here, boundary here, boundary here. These are crystal boundaries or grain boundaries, as we tend to call them. And what does it mean, twins? Look here. Look at this plane of atoms, and it continues here, like a mirror image, right? And this continues here, like a mirror image. And this continues here, like a mirror image, and so on and so forth. Neglect the sigma signs. It's not important now. So this is what I thought I have. Now, this is just a computer drawing of the same thing. Now, if you take a diffraction pattern for one of them, you would have a periodic diffraction pattern, because the structure is periodic. If you take a diffraction pattern, now this was number one. If you take from number two, you'll get the same diffraction pattern, but it will be rotated 72 degrees. 360 divided by 5, 72 degrees. And then the next one, 72 degrees again. But if you take diffraction pattern from all of them together, then you will have 5 superimposed diffraction patterns, and obviously it will have a 5-fold rotational symmetry, and this is what I thought I had. But as I told you, I could not find the twins. Okay. This was the beginning. In 1994, I published the first paper with Professor Ilan Blech, who was a professor at the Technion. His contribution was very important because he designed the first model, called the Blech model, to explain how such material could have been created. I sent this paper to a journal called Journal of Applied Physics. Those days, the youngsters amongst you don't even imagine how it was to send a paper for publication. You had to have it typed. I didn't say we typed it. We couldn't type. We had secretaries that typed for us. And my secretary typed that paper. I made the corrections. He typed that paper again. I made another correction. He typed this paper again and again and again. Finally, I had the final version. Put it in an envelope, put a stamp on it, and wrote the address, nice handwriting, and sent it to Journal of Applied Physics. 2 weeks later, I received it back in another envelope with a letter saying something like the following. Dear Dr. Shechtman, thank you so much for your contribution. We have decided not to send it for review because we think that it will not interest the community of physicists. Okay, so I put it in another envelope, sent it to another journal called Metallurgical Transactions. They accepted it and they published it. But they published it 8 months later. It's a slow publication journal. It took them so many months to publish it, and it was published in June 1985. I sent it like in October or something of 1984. So this was paper number one. And then my host, again, by the way, I didn't mention, which I should, I made a discovery when I was on sabbatical at NBS, National Bureau of Standards, in Maryland, near Washington, D.C. My host was Professor John Kahn, and I showed him the paper that was rejected and asked him, what's wrong with this paper? Well, what do you think it was rejected? John says, oh, Danny, you'll have something fantastic here. Let's do something completely different, write a short version of the same paper and send it to a quick publication, PRL, Physical Review Letters. This is what we did. We sent it. It was accepted in a few weeks, and in November 12, 1984, it was published. And when this paper was published, hell broke loose. Because from all over the world, I started to receive emails and telephone, Danny, we have it, this is fantastic. Because I explained exactly how I prepared the specimens, people could repeat it in a couple of days, put it in the microscope, voila, exactly the same results. In no time, there was a community of young avant-garde scientists that grew very, very fast around the world, studying quasi-periodic materials, and they took my discovery and turned it into a thriving science. And it all happened very, very quickly. Okay, Now, icosahedral symmetry. What is icosahedral symmetry? This is an icosahedron. It's a platonic body. This, by the way, is a specimen made of wood. A friend of mine made it for me. And many of the quasi-periodic crystals have icosahedral symmetry. Not all of them. There are many kinds of them. So this is an icosahedron. So what's special about it? Now, if you look from here, put your eye here and look to the center, you'll see that it has 5-fold rotation symmetry here. If you look your eye here, exactly where you are, you see that there is a 3-fold rotation symmetry. If you put your eye here and look to the center, you'll see a 2-fold rotation symmetry. And the angles between the axes are exactly the angles in my diffraction patterns. So my diffraction pattern showed an icosahedral symmetry, and this is why we called it the icosahedral phase. And this is an icosahedron. It has 6 5-fold axes. Let me show you. 1, 2, 3, 4, 5, 6. This is just the negative of that, so we don't count it. 6 of them, and so on. Okay. Now, let me show you another way of looking at icosahedral symmetry, and many of you will like that one. This is a football. How do you call it in this country? A football or? Football. Not like in the United States. It's soccer, as you know. Now, it's a football, and as you see, it's composed of patches of pentagons and hexagons sewed together. 5-fold symmetry if you look this way, 2-fold symmetry if you look this way, 3-fold symmetry if you look this way, and I can promise you that even the best team in Australia doesn't know that they play with icosahedral symmetry. You may ask them, you'll see. Okay. Now, what is quasi-periodicity? This is the main issue. What is quasi-periodicity? In order to understand quasi-periodicity, let me take you back to the 13th century and meet Mr. Leonardo Fibonacci de Pisa, the greatest mathematician of his time, and probably hundreds of years later, he was still the greatest mathematician. So this is him. This is a drawing. Look at his eyes. Bright guy. And this is a real picture of a statue that was erected in his memory. And this statue is just behind the inclined tower of Pisa. Just behind it, 50 meters or 100 meters behind it, there is a graveyard under a roof. And this statue is there. So if you go to visit the inclined tower of Pisa, pay a visit, look at his statue, because he was such an important person. So this is him. So what is quasi-periodicity? To understand quasi-periodicity in one dimension, I will take you now to an experiment that he proposed, which is called Fibonacci rabbits. Yes. So this is quasi-periodicity in one dimension. These are Fibonacci rabbits. What is the story? Fibonacci proposed the following. In the first month, we have a female rabbit. She has a husband or boyfriend, whatever, and in the second month, she gives birth to a little one. In the third month, same thing occurs. She gives birth to a little one, but this little one has to mature 1 month, so it grows. In the fourth month, this mother gives birth to a little one, this little one matures, and this mother gives birth to a little one, and so on and so forth. I'll take you one more. This mother gives birth to a little one here. This little one matures. This mother gives birth to a little one, and this mother gives birth to a little one, and this little one matures. So now that you understand how to continue it, surely there is order. You know how to continue this series. So there is order there. But what about periodicity? Look here. By the way, I stopped here because this was the end of the page. No, that's a fact. So let's look for periodicity. It seems that we have it, but really we don't. Look here. Large, small, large, large, small, large, small, large, large, small, but large, large, small, large, small, large, large, small. There is no periodicity at all. There is no motif of any size which repeats itself periodically in the Fibonacci series. And yet there is order. There is order. There is no periodicity. This is quasi-periodic order in one dimension. Now, Mr. Fibonacci published it, by the way, what is this? These are the two equations that you need to understand. It's quite extremely simple. What does it say? The first equation says that the number of rabbits in the nth month equals the sum of the number of rabbits in the 2 previous months. These are the number of rabbits. 1, 2, 3, 5, 8, 13, 21, you can count them. So 1 plus 2 is 3. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21, we will have 34. 21 plus 34, we'll have 55, and so on and so forth. These are called Fibonacci numbers. Okay. This equation said the following. If you go to infinity, then you divide the number of rabbits in the last row by the one before it, you will have an irrational number, which is this number, 1 plus root 5 divided by 2, which is an irrational number, and it's called Fibonacci number, or the golden mean. Why is it called the golden mean? Because people who understand in aesthetics never argue with people who understand aesthetics. I mean, you lose. People who understand aesthetics, so they claim, tell you that this ratio is very beautiful. So if you look at the Mona Lisa and divide the distance between her eye and her nose by the distance between her eyes and the mouth, you'll get the Fibonacci number tau, and so on and so forth. This is why it's called the golden mean. Okay, but that's besides the point. So this is the Fibonacci number tau. And he published it in the year 1202, the beginning of the 13th century, in a book called Liber Abaci. Liber Abaci, Book of Abacus, or Book of Mathematics. Now, it's interesting. This book was not aimed to publish that. This is just a side chapter in that book. That book was important in another way. You see, Leonardo Fibonacci di Pisa tried to convince the merchants of Pisa not to use the Roman numerals to do calculations, because it's almost impossible. Use the Indo numerals, the numerals that came from India, which we use today, to do mathematics. And this book was dedicated to that, and he showed how easy it is to do mathematics if you use what we call now modern numerals, such as 1, 2, 0, 2, like this. Okay. What about quasi-periodicity in 2 dimensions? Here I take you to Penrose tiles. Roger Penrose is an eminent scientist living in our time. He's an amazing scientist, a physicist, philosopher, crystallographer, you name it. And he's living in England. And he designed the Penrose tiles, 2-dimensional tiles, 72 degrees, 36 degrees. And if you join them together according to certain matching rules, there are rules how to match them together. If you follow that, by the way, the matching rules are simple. You join one arrow with one arrow in the same direction, 2 arrows with 2 arrows in the same direction. Voila, you have it. That's all. Then you create the Penrose tiling. Now, what's interesting with this Penrose tiling, it's quasi-periodicity in 2 dimensions. There is no motif that repeats itself in all this 2-dimensional space. And there is another scientist named Alan Mackay, who is a crystallographer, also living in England, who showed that if you take a diffraction pattern from Penrose tiles, you will have a 5-fold rotation pattern with sharp points. So he did that before the discovery of quasi-periodic crystal, but he published it in an obscure Russian journal, so very few people knew about it. Although Penrose tiles were very well known because they were published in many forms. Okay, so this is quasi-periodicity in 2 dimensions. What about quasi-periodicity in 3 dimensions? Well, here goes. These are quasi-periodic crystals, and this is one such crystal from the magnesium-zinc cerium composition, and you can clearly see beautiful 5-fold symmetry facets on it, and so on and so forth. So this is quasi-periodicity in 3 dimensions, all of them in real space. Okay, now I want to talk a little bit to the mathematicians among you. I know that there is one here. I'm sure that there are many others, but everybody will enjoy it. Look, and this will answer many questions. It's called cut and project. This is a little bit science on top of all these stories that I told you. It says the following. You can take a high-dimensional periodic space, make a cut and project it, and you will receive a quasi-periodic space in a lower dimension. Don't faint, I will explain it. Here we have a two-dimensional periodic space. Right? Let's assume that in every intersection, there's a mathematical point. It means a point without dimension, just a point there. Okay. And now what we can do, we can make a cut in it. A cut is just a strip like this. See, we start in a point here, and we start in a point here, and send this strip upwards, but not in any direction. I chose to send it in the direction such as that the tangent of alpha, which means this divided by this, is the Fibonacci number tau. All right? Wonderful. So what I'm telling you now the following. This line, who started in a point here, will never, ever meet any other point. Never. Why so? Because if it met another point, let's say that it met this point here. It looks like it met this point here, although it doesn't. Then the tangent will be this number divided by this number, which is a rational number. But I sent it into an irrational number. It will never meet any other point. So this is the cut. Now I can choose all the points inside and project them onto the one-dimensional space, which is this line. And look what we have received. We have large distance, large, small, large, large, small, large, large, small, large, small, large, large. We have created a Fibonacci series, which we know is quasi-periodic. So what did we do? We took a high-dimensional space. How high? Two-dimensional space. We made a cut. We made a projection. And we received, on a lower dimensional space, on this one-dimensional space, we received a quasi-periodic array, from periodicity to quasi-periodicity. Now, if you have time this evening, if you want to play with it, then you can take a six-dimensional space, make a cut in it, and project it onto a three-dimensional space, and then you have created a new quasi-periodic order, or quasi-periodic crystal, if you wish, in 3 dimensions. Does it exist? Maybe it does, maybe it doesn't. Depends on what ordered structure you took in 6 dimensions. Just if you have time this evening. Now, let me show you something which is really interesting and applied. I repeat what I did before. This is the cut. This is alpha. Tangent of alpha is a Fibonacci number. Now I bring up red lines. The red lines are almost like the black lines, but they are not quite there. I made them a little different so that tangent of red alpha is periodic. I made this point meet here. I made this line meet this point here, and the tangent is 11. You can count it, divided by 7. This is a rational number. It's close. It's 1.57, while this is 1.61. But it's not right there. Okay. There are many crystals with very high unit cell. Look at the size of unit cell here, from here to here. Okay, this is 1, and then there will be 2 and 3 and 4. Large unit cell, there are materials like this, which are almost quasi-periodic, but not quite. They are periodic. These are called approximants. They are very proud to be approximately quasi-periodic. And they have very interesting properties, and many people study these approximants. So it's a totally different subject, but it came out from quasi-periodicity. Now, forget about science, let's talk about the story. Take you back to the story. And the first in the story are years of rejection. I started to talk about my findings, 5-fold rotation symmetry diffraction pattern, and all kinds of strange things like this while I was on sabbatical. The reaction of my peers in the corridor diverted from support to total rejection. Give you a few examples. My host, John Kahn, was coming to my office and said, Danny, we have something fantastic here. And I challenge you to find out what it is. Encouraging. He didn't solve the problem, but it was encouraging. The other end was my laboratory head of my laboratory, who came to my office one day, smiling sheepishly, putting a book of X-ray crystallography on my desk, saying, "Dear Dr. Shechtman, please read this book, and you will understand that what you are talking about cannot be." And I said, "You know, I teach at the Technion. I know this book very well. I don't need to read it. I'm telling you, my material is not in the book." Took the book back, came back a few days later. I said, "Dr. Shechtman, you're a shame to my group. I'd like you to leave my group. I cannot have my name associated with yours." So I left the group. Now, don't faint. It didn't mean much, but instead of reporting to his secretary, I reported to another secretary of another laboratory head who adopted the scientific orphan. I stayed in my office, I stayed in my laboratory, and it was just an episode, but this was the range of reactions from positive support to total negative, and everybody else was in between somewhere. People were laughing in my face, people were laughing behind my back. It was a little bit unpleasant. And if you want to know how I felt during that period of time, it was something like that. Okay, so this was first. Then came 1984, we published the first paper, and now the main rejection came from the International Union of Crystallography. You remember that the tool of choice was X-ray diffraction. And myself and my colleagues did not have X-ray diffraction patterns from a single quasi-periodic crystals. Why couldn't we have it? Because they were very, very small. And those days, we did not have small enough beam, which we have today, to take a diffraction pattern from a crystal which is 1 micron in size. We needed to grow larger crystals. But in order to grow large crystals, we needed a stable composition, so from which you can grow large crystals. As large as 1 millimeter is good enough. We didn't have it. But in 1987, my colleagues, not me, from France and from Japan, sent me beautiful X-ray diffraction patterns from a single quasi-periodic crystal. And I showed these pictures in a meeting of the International Union of Crystallography in 1987, and that meeting was in Perth, Australia, right here, 1987. And these were the pictures. So beautiful Laue patterns, 5-fold. See the 5-fold symmetry, 3-fold, 2-fold, beautiful pictures. And when I showed this slide, the community said, "Okay, Danny, now you're talking." And they created a committee. The International Union of Crystallography created a committee, and that committee redefined crystal. And I have shown you the definition in the beginning of my talk. 1987. Okay, here in Perth. Okay, so you would think that now, I mean, the International Union of Crystallography approves the existence of quasi-periodic materials. Who will object? Not so fast. Because there was Professor Linus Pauling. Now, Professor Linus Pauling was arguably the greatest chemist of the 20th century. I mean, he was really, really a great chemist. He taught us so many things. He lacked one thing. He was not humble. And this is a major understatement. Professor Linus Pauling thought he understood everything. Nobody does. And he took it upon himself to prove that what I was saying and my colleagues were saying is wrong. And he was a very flamboyant speaker. Some of you may have seen him talk. I mean, he was an amazing speaker. And he stood on stage just waving hands and said, "Dan Shechtman is talking nonsense. No quasi-crystals, just quasi-scientists." Everybody was clapping hands. Okay. But the arguments with him, and I had a lot of correspondence with him over the years. I met him twice, once in 1980-something, I forget when it was, in the meeting of the American Physical Society. And then I came to visit him in his home in Palo Alto and gave him a talk like this for one person. There was one person in the audience. He was sitting there on the couch, and I gave him a talk with slides. Anybody remember the slides in the cassette? Ah, yeah. So this is, I gave him a talk of 1 hour. At the end of the talk, he said, Dr. Shechtman, I don't know how you do that. Because he did not understand electron microscopy. There you go. He tried to prove time and again that our model was wrong. Now, you remember the Cotton project? You remember the approximants? He designed approximants, one after the other. Each one was larger in size, so it got closer and closer and closer to being quasi-periodic. But if you design something periodic, you cannot make it quasi-periodic. You can come closer and closer and closer. Imagine that somebody says that the number pi is a rational number. Really? Prove it. Okay, no problem. I draw a circle. I draw the diameter. I measure this, divide by this. Rational number. You say, yeah, okay. So it's 3.14, but that's not exactly pi, right? He said, no problem. I draw a larger crystal. I draw a larger circle. He made a larger crystal, and a larger crystal, and a larger crystal. But he could never get quasi-periodicity this way. He insisted on rational numbers, and that was his major mistake. Anyway, Linus Pauling continues to fight his battle for 10 years, 1984, 1994. But in August 1934, he died, and that was the end of rejection by him and by his followers. Well, it's not nice to laugh when somebody dies. No, it's not nice at all. Anyway, I want to summarize by doing a few things. Number one, I want to mention a few people who made seminal contributions. Roger Penrose and Alan Mackay. Roger Penrose, who designed a two-fold quasi-periodic array by Penrose tiles. Alan Mackay, who showed that if you take a diffraction pattern from that, or if you do a Fourier transform of that, you'll have sharp diffraction patterns in the reciprocal space with five-fold rotational symmetry. Ilan Blech, Denis Gratias, and John Kahn wrote the papers with me. John Kahn was my host. Denis Gratias was a visiting scientist from France, at that time from a laboratory in Vitry. He's still in France in another laboratory. Ilan Blech was the Israeli who wrote the first paper with me. And Dov Levin and Paul Steinhardt, these are two people who designed a mathematical model based on three-dimensional tiles, as opposed to the Ilan Blech model that is based on joining icosahedron in space. Basically, it's the same thing, but different approaches. Okay, now relax. This is an interesting drawing that will show you what I felt those years. This drawing was made by a colleague of mine at NBS in the summer of 1986, and I came there every summer. He brought it to the dining table at lunch. I confiscated it from him, and this is why it remains to be part of history. And what does it say? See, this is the month, in 1986, January, February, March, April, and so on. Okay. This number is 1 over n. What is n? N is the number of pages in the bibliography. We hired a secretary that collected all the papers on quasi-periodic materials, and she created a library, file after file, and she prepared a bibliography. So let's say that on each page we had 20 papers, page after page. So n is the number of pages. If we had 1 page, we have 20 papers. If we have 10 pages, we have 200 papers. Okay, this is the number of pages. And 1 over n is just 1 over n. So what do we see here? 0.1 means 200 papers, right? Because n is 10. 10 times 20 is 200 papers, and so on and so forth. The number grows and grows and grows here. He just counted the number of papers in February of 1986, in March of 1986, in April, and so on. I came there in July. As a good scientist, he connected all these points with a straight line, and to our horror, we realized that by December of 1986, the number of papers published on quasi-periodic materials will reach infinity. And we will have to cut all the forests in the Amazon just to provide papers, to print all these. It didn't happen, but the feeling was that the world is exploding around us with activity. It was an amazing period. Okay, I want to summarize. While as before order was synonym to periodicity, now we know that order in crystals can be periodic or can be quasi-periodic. So this was the paradigm shift. And I would like to give you time for questions, but I would like to ask the first question and answer it, and then you can ask questions, okay? So my question is, and I'm sure that some of you also may ask the same question, why is it that quasi-periodic crystals were never discovered before 1982? Why is it? Why did it take 70 years of crystallography to discover quasi-periodic crystals? Is it because they're very rare? Maybe they're not stable? Is it because they're difficult to make? Is it because they're made of rare elements, praseodymium, gadolinium, and a touch of zinc? What is it? Why was it so difficult to discover them? Well, are they rare? Quasi-periodic crystals are not rare at all. There are hundreds of them. Here is a little partial list of compositions which are quasi-periodic based on aluminum alone. So you find them in the aluminum cobalt system, aluminum chromium, germanium, aluminum chromium silicon, and so on. So endless number, hundreds of them. Somebody could have stumbled upon one of the hundreds, and they didn't. Why? This was not the reason. Are they not stable? Many are not stable. But what does it mean? I prepared my samples by rapid solidification. This was a metastable material. It is stable at room temperature, but if you raise the temperature to 400 degrees C, then it will transform into a periodic phase. But at room temperature, stable, anybody could study it. And there are stable quasi-periodic materials based on aluminum, lithium, copper system, and so on. So they are stable. Stable means that they melt congruently. Melting congruently means that you heat them up to the melting point and they do not transform on the way to anything else. This is congruent melting. So there are stable ones, quasi-metastable ones, and nobody ever discovered them before. Okay, are they difficult to make? And I, with my magic fingers, made one of them. Not at all. They are very easy to make. You can make them by casting. You can make them by rapid solidification. You can make it by single crystal growth, electrodeposition, CVD, PVD. Any method you prepare solid materials, you can make quasi-periodic materials. It's easy, very easy to make. Fact is that a couple of days after I announced my discovery, people had it already. Very easy to make. That's not the reason people did not discover it before. Are they made of rare elements? Not at all. They are made of iron, aluminum, chromium, copper, titanium. Millions of tons of these elements are used every year around the world. So what is it? Why quasi-periodic materials were never discovered before 1982? This was the question. Now I'll give you my answer. And my answer is divided into several parts. Part one, quasi-periodic materials had to be discovered by transmission electron microscopy because the crystals were too small. Now, if you take the same material and you take an X-ray diffraction pattern for many crystals, because the beam was large, then you will have rings in the diffraction pattern, and you cannot identify the five-fold rotation symmetry, you cannot discover quasi-periodic material. Okay, so TM, transmission electron microscopy, was essential for the discovery. So you may rightly ask, okay, big deal, Dan Shechtman, you are not the only electron microscopist in the world. There are thousands upon thousands of people who use electron microscopy all over the world. Why you? Well, it takes more than just working on the TEM, you have to be a professional. A professional microscopist, electron microscopist, transmission electron microscopist, is somebody who knows very well crystallography, somebody who knows to use the microscope well, somebody who knows to analyze diffraction patterns and defects in crystals very well, and there are not very many of them. You'll be very surprised. Let me give you an example. My laboratory at the Technion in Israel is probably the oldest and best TEM laboratory in Israel. We are there since 1967, very many years. And over that period of time, although thousands of students and researchers worked on the microscope, we have produced maybe 15 professional electron microscopists. 15. Over so many years, out of thousands of people who work with the microscope. Why so? There are several reasons. Number one, usually an hour on the microscope is expensive, and the professors don't like to pay a lot of money. So if it costs $100 per hour, professor will tell his student, okay, you take 5 hours, get some pictures, put it into your dissertation, and go and measure the thermodynamic properties of your material. Well, so this group cannot be professional. In order to become professional electron microscopists, you have to work for hundreds upon hundreds upon hundreds of hours on the microscope. Know not only the operational, but know the theory to the extent that you can teach transmission electron microscopy, and I was that person. I taught classes all over the world of transmission electron microscopy. So it takes professionalism. And my message to the young among you, remember the first one was to write everything in a logbook? Message number 2, if you want to succeed in your academic career, then you have to have 2 features. Number 1, broad knowledge of the laws of nature, and 1 peak of expertise. And I promise you, if you have broad knowledge of the laws of nature, and if you have 1 peak of expertise in something that you like, you'll have a wonderful scientific career. Okay, so you have to work on the transmission microscope, you have to be a professional, you have to have tenacity. What does it mean, tenacity? Tenacity means be like a Rottweiler dog. You find something interesting, you bite, you don't let go. Just stay on it until you find what it is. Here is an example, counterexample. There's one person whom I know who saw my 5-fold diffraction pattern before me. How do I know that? His professor told me later in years. You know, he called me one day and said, "No, Danny, my student, so-and-so, he had your diffraction pattern before you." I said, "Wow, what did he do with it?" He said, "He filed it." Said the professor, "I found it. I went through my ex-students' files and found your diffraction pattern right there." I called my ex-student. "Hello, my ex-student. How are you doing?" "Thank you, professor. I'm fine. How are you?" Said the professor, "You know, you saw Dan Shechtman's diffraction pattern before him." Said the student, "Of course I know." Said the professor, "Why didn't you tell me?" Said the student, "You know, professor, if I told you, you would want me to stay for 2 more years on my PhD." He filed it. He's an excellent scientist. I met him recently. We knew about each other, of course. We hugged each other when we met. He's a wonderful scientist. He works for the industry. He's a great person. But he did not have tenacity. Don't let go. Believing in yourself. You can believe in yourself if you're a professional in something, to the extent that if the top of the scientific community tells you you are wrong, you stand tall and say the following: "If you want to prove that I am wrong, repeat my experiments, or if you are a theoretician, repeat my calculations, show me what's wrong. Don't tell me it is not in the books. That's not good enough. You cannot discover anything if you go only for what's in the books. Repeat what I did, show me what went wrong. I'm listening." Nobody did that. Okay. So believing in yourself and resilience. Resilience means having enough patience. You know, in the first years, my promotions were delayed. Many people said I talk nonsense, and just as an anecdote, there was one professor in my department who hated my guts. Why would anybody hate me? I mean, but he did. And when I was up for promotion, he flew to Palo Alto to talk to Professor Linus Pauling. And he wrote to the rector of our university, it's not me, it's just that I just spoke to this eminent god of science, Linus Pauling, and he says that Dan Shechtman is talking nonsense. How can you promote such a person? When my provost received this letter, he said, we promote you tomorrow. Because he knew that professor. Okay, so resilience. This is it. This is my answer. Thank you very much. Fabulous. Thank you. Thanks.
Wow. The only word for that, as a chemist, that was just beautiful, Danny. It was just beautiful. Anyway, we have time for questions. Who's going to start off? Over here? Just wait till the microphone comes so everyone can hear your question.
I will come to you and listen.
Use the microphone.
Have any QCs been observed in nature?
Quasi-periodicity in nature. Okay. Well, I can tell you that the Fibonacci number appears in nature in many ways. Fibonacci spirals are typical for snails who build sea or land, the creatures that build their shells, and these Fibonacci numbers there. Many trees will build branches in a Fibonacci sequence, again a Fibonacci spiral, and there are several other places in which it appears. So yes, it's a quasi-periodicity in a way. Nature likes quasi-periodicity in certain instances, right? Other questions?
Next question. We've got a second one back.
This, by the way, the little chap is our number 10th grandchild.
Thank you for your excellent work. My question is because you already discovered for quasi-crystal, that's
what?
based on the alloys. Was there anything new for just a single element material which can find for quasi-crystal?
Okay.
Thank you.
I will make your question broader. Can we predict a composition that will create quasi-periodicity? Is that good?
Because
or is there a certain element?
It's just a single element. Because you say aluminum, manganese, you would say just find aluminum or copper, some just a single element, or the pure element can find any quasi-crystal. No.
Right. No.
No.
No. Thank you.
All right, next question. Yeah, we've got the lady just across. Yep.
Excuse me, I had two questions. You already answered one of them. The first one is, how did your teachers mean to you in your life, professional life?
How did my teacher affect my professional life?
Yeah.
Good question, yes, and?
Yeah. The next one was about your failures and how you deal with them, but you already, I think, answered them.
So you want only one answer. How did my teacher affect my life? Okay. This is an important question because we are in an academic educational institution, and I want to mention something about teachers. And first, answering your questions, I will give you an example. When I was in high school, my physics professor drew on the board a series of resistors, electrical resistors, connected each and every way. It was a whole bundle of resistors. And he asked the class, what is the resistivity from this end to this end? Right? So there were resistors connected parallel and in series. And I raised my hand, and I came to the board, and I solved this question. And the professors and the teacher in physics says to the class, Dan understands physics. This was 60 years ago, and I remember it. Encouraging a student when it is worthy, when the student deserves it, is very important at any age. Not only a student, a child, your children. Encouraging young people, not on everything, but when they really deserve it, is absorbed. It says, I have approval from the elders that I am good. I would like to continue to be even better. I will continue this line. Right? Okay, encourage your students when they deserve encouragement. This is very, very important.
And there was a question at the front there.
I'm not a crystallographer, but I had just a question. Does quasi-crystal always have a diffraction pattern, or is it only certain quasi-crystals?
Right. So the question is, do quasi-periodic crystals have always a diffraction pattern? And the answer is, of course, yes. You see, if you have an ordered system, then the Fourier transform will give you sharp points, regardless of whether it's periodic or quasi-periodic. So the answer is definitely yes.
And just at the back there, second one back.
Thank you very much for your educational lecture. I'm a medical scientist. There are so many viruses that has the structure of quasi in terms of their protein structures. Based on your expertise, what is the advantage for the materials have such characteristics? Okay. What's the advantage in the
viruses? Like, I'll give you an example, like the adenovirus, for instance, whom I'm sure you know, and many of you know, has an icosahedral symmetry. It's a one molecule. It's not a crystal. All right? A crystal is many, many molecules or many, many atoms that create an order. Viruses have a core, such as I mentioned, the adenovirus, which is icosahedral, but this is one molecule. It's not a crystal. All right? It's one molecule. You can create molecules. You can create crystals for molecules. Not only can you create, people do it all the time because this is the way people now study proteins. I mean, how now people identify proteins by creating crystals made of molecules, such as quasi-periodic, or such as icosahedral molecules. If you create a crystal from them, that crystal, in most cases, in all cases that I know, will be periodic. Tuck, 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 tuck. You make a crystal. Once you make a crystal, you go to a synchrotron, and you analyze the position of every atom in that molecule. It's an amazing technique, really amazing technique. But one virus is one molecule. It's not a crystal.
So we've got time for one more question, and we'll take that one over there. Mike's just behind you.
First of all, thank you so much for your very inspiring talk. And I would like to mention that it is an honor for me and, of course, I'm sure for many others to be in this presentation today. My question is about the crystallization reaction itself. Although you mentioned this is very simple, I mean, crystallization is a simple process. But to make crystals with this quasi-crystal order, do we need to have some specific reaction conditions in terms of physical or chemical conditions for the reaction? And I have a very brief follow-up question as well. Do you think this is going to be the end of the findings in crystallography, or we should expect further discoveries if we have more advanced technologies in future? Thank you so much.
Okay, thank you for your 2 questions. I'll answer number 2. The answer is no. There's never end. There's never end to science. Your grandchildren can be scientists, and they will have plenty of work to do. And their grandchildren will also have plenty of work to do. There's endless work in order to understand nature. And what we know is that there are so many things we don't know. So the other question is there any specific reaction? Are you a chemist?
I'm a natural scientist.
Okay. Now, quasi-periodic crystals are built. While they are built, let's say that you have a melt, the composition of which will create quasi-periodic crystals. So you have atoms running around in this order. They are not ordered at all in the melt. And this melt starts to solidify. Right? Then the atoms would like to find a spot where they will have minimum free energy. Right? And they form quasi-periodic crystal just as they do form periodic crystal, because for this specific composition, forming quasi-periodic arrangements has minimum free energy. So it is governed by thermodynamics, and that's it. That's all there is to it. There is nothing special beyond that. Okay,
so it falls for me to make a very brief vote of thanks. Danny, that was original, beautiful research, but actually it was delivered beautifully. It was just a delight to listen to it. I found it interesting, it was intriguing, it was informative, it was insightful, and for those of us who have taught or will be teaching students, what a lesson in how to get over something that seemed very simple to us listening, but the underlying stuff, it's, the maths, the rabbit's brilliant way of doing it. We've been privileged to be in the presence of Danny today and to hear what really was a tremendous lecture, a marvellous lecture. Danny, thank you very much, and please accept this small gift from us.
Thank you all. Thank you very much. Thank you.